Greetings! The objective of this video is to provide a slow description of some of the work entitled On the Opportunities and Risks of Foundation Models. This work was published on arxiv by Bommasani et al. In 2021. The paper is extensive, spanning 212 pages, and in this video we will focus our attention on the introduction, which outlines the key themes for the rest of the work. In addition to its length, a couple of other points make this paper different from many others spanning the machine learning domain. First, it involved an experimental, distributed writing effort from many teams of authors spanning many different disciplines. Second, the paper includes a disclaimer, which I will preserve here, that not all views expressed in the report are held by all of the authors. Here's an outline for what will be covered in the video. First, we will start by defining foundation models and discussing where they have come from. Next, we will discuss the potential social impact of these models and the broader foundation model ecosystem. We will then turn to the question of norms and incentives, as well as the role played by academia in the development of foundation models. Finally, we will outline the structure of the remaining Stanford report on foundation models, discuss some of the responses and critiques of the report, as well as provide pointers for further material. Okay, then let's dive in. Let's start at the very beginning. What is a foundation model? A foundation model is a model trained at broad scale that can be adapted to a wide range of downstream tasks. Examples of such models that have been developed to date include BERT, GPT-3, and CLIP. It's worth noting that the technology behind foundation models is not new. It is essentially self-supervised learning with neural networks, which have been around for decades. What is new is the scale of recent models and their ability to perform tasks that go beyond their training regime. There are two key ideas that underpin the significance of foundation models. The first is emergence. Emergence refers to the fact that system behavior is implicitly induced rather than explicitly constructed. Emergence is the cause of a great deal of scientific excitement, but also anxiety about unanticipated consequences. The second idea is homogenization. Homogenization refers to the consolidation of methodology for building machine learning systems across many applications. Homogenization provides strong leverage for many tasks, but also creates single points of failure. These concepts of emergence and homogenization can be understood within the broader story of AI development. With machine learning, how a task is performed emerges from examples. With deep learning, which fits within machine learning, what emerges are the set of features used to perform prediction, while with foundation models, what emerges are new functionalities like in-context learning. With regard to the second concept, machine learning represents a step towards homogenization of learning algorithms, since a single algorithm, such as logistic regression, can power a wide range of applications. In deep learning, rather than designing separate features for each application, the same architecture can be used. With foundation models, the same model can be used for a wide range of tasks. Since these ideas can seem a little abstract, let's make them more concrete with examples. First, note that modern approaches to building AI systems tend to make heavy use of machine learning. The key ideas behind machine learning, or ML, have been around for some time, stretching back to at least the work of Alan Turing and Arthur Samuel in the mid-20th century. and much further still, depending on how you choose to define the term. However, machine learning really started to become popular in the 1990s, where it represented a significant shift in how AI systems were built. A key theme of ML, in contrast to previous rule-based systems, was that it did not specify how to solve a task. Instead, the how emerges from the learning process. Machine learning also represents a kind of step towards homogenization, since many applications could now be powered by the same learning algorithm, rather than establishing separate rule sets for each application. Note, however, that complex tasks in natural language processing and computer vision still relied heavily on domain experts who would perform feature engineering to design features such as SIFT that would provide the learning algorithm with inputs that were easy to learn from for good performance. Within machine learning, slightly more than a decade ago, there was a resurgence of ideas in deep learning. Beyond the original algorithms, which had been developed much earlier, key factors that drove this resurgence included GPUs that provided the necessary computation and increased data availability, largely thanks to the internet. These combined to produce breakthrough results like AlexNet in the 2012 ImageNet competition, which went far beyond any previous methods in terms of performance. Deep learning also represented a second form of shift towards homogenization. Rather than requiring handcrafted, bespoke features from domain experts, now the same architecture could be used widely across a range of applications. Let's now look at some of the background behind foundation models. Foundation models are enabled by a process known as transfer learning, in which we take knowledge from one task, for example, object recognition in images, and then apply it to another task, like activity recognition in videos. Within the field of deep learning, the dominant paradigm for transfer learning has been to use pre-training, in which we first train a model on a surrogate task to learn good representations, and then perform adaptation by fine-tuning on a given task of interest. What has made foundation models particularly powerful transfer learners is their scale. 3 ingredients, in particular, have gone into their scaling. The first has been computer hardware improvements, notably GPUs and larger memory. The second has been the introduction of transformer architectures, which are particularly effective at leveraging hardware parallelism and providing expressivity. The third has been the growing availability of training data. Some, though by no means all, of the influential early successes of transfer learning came from supervised pre-training on datasets like ImageNet, which provided large numbers of images annotated with fine-grained labels. However, the cost of annotation makes it difficult to scale up supervised pre-training, limiting the benefits of this approach. In self-supervised learning, on the other hand, the pre-training task is derived directly from the data without the need to perform annotation. For example, BERT is trained to predict masked words from their context. We can build training data for BERT by taking a potentially contentious phrase like "I like Brussels sprouts" and masking one word randomly, in this case, the word Brussels. We can then train the model by providing the masked phrase as input and requiring it to predict the target from its context. Self-supervised methods like this are inherently more scalable than supervised methods, since they have no associated labeling costs. They also provide a potentially richer learning signal. This is because the model is tasked with predicting part of the inputs, which can be very diverse, rather than a manually curated label space, which is typically more limited to ensure that the annotation process is practical. The use of self-supervision has proven to be particularly productive in the field of natural language processing. One theme of prior work has focused on learning word embeddings, which are trained to associate words with context-independent vectors, with notable examples including word representations, word2vec, and glove, each of which can then be applied to downstream tasks. Another theme has focused on autoregressive language modeling as a pre-training stage to produce contextual representations, with sequence-to-sequence language model pre-training and methods such as GPT, Elmo, and ULM-Fit. Then, following the introduction of transformers, there has been a surge of methods like BERT, GPT-2, Roberta, T5, and BART, demonstrating the strong gains in performance that can be achieved by coupling self-supervision with the transformer architecture. One interesting development occurred around the time that BERT was introduced. Bommasani et al. Note that, prior to 2019, self-supervised learning was essentially a sub-area of NLP. However, after 2019, self-supervised learning with language models had essentially become a substrate of NLP, with use of BERT becoming the norm rather than the exception. This acceptance of the use of a single model for a broad range of tasks effectively marks the start of the modern foundation model era. One of the most notable characteristics of foundation models is that they produce massive levels of homogenization, since almost all state-of-the-art NLP models are adapted from just a handful of source models like BERT and T5. This has a significant benefit in terms of leverage, since any improvements in the foundation model yield gains across much of the NLP landscape. On the other hand, it also represents a significant liability, since all systems can inherit the biases of a few foundation models. Looking beyond NLP, foundation models are also producing increasing homogenization across research communities, with transformer-based sequence models applied to text, images, speech, tabular data, protein sequences, organic molecules, and reinforcement learning. These examples suggest a potential future of unified tools for developing foundation models that span a range of modalities. As part of this trend, there has also been a homogenization of individual models across communities in the form of multimodal foundation models. Prominent examples of such models include CLIP and DALI in the domain of vision and language. Since for domains like healthcare, where the data is naturally multimodal, often including medical images, structured data, and clinical text, multimodal foundation models are, in some sense, a natural fit. One of the great benefits of multimodal foundation models is that they can ingest data from across domains such as text, images, speech, structured data, and 3D signals, and make use of all of these as training data to produce a single foundation model. This model can then be adapted to a broad range of downstream tasks like question answering, sentiment analysis, information extraction, image captioning, object recognition, and instruction following. Scale has played an absolutely key role in the emergence of new abilities in foundation models. As an example, GPT-3, a model with 175 billion parameters, enables in-context learning, which describes the process of adapting the model to a downstream task simply by providing it with a prompt that describes the task in natural language. This is an emergent property that was not explicitly programmed into the model and was not observed with the smaller GPT-2 model containing 1.5 billion parameters. It's worth noting that homogenization and emergence can potentially interact in a rather unsettling manner. While homogenization can bring gains where task-specific data is limited in domains such as healthcare, it has the risk that any flaws in the model are inherited by all adapted models. Moreover, since the power of foundation model derives from their emergent properties, they are naturally hard to understand and have unexpected failure modes. It therefore perhaps goes without saying that since emergence generates significant uncertainty about what the true capabilities and flaws of foundation models are, a strategy of aggressive homogenization in which everyone builds on the same model is particularly risky. In fact, the authors of this work suggest that de-risking is the central challenge in developing foundation models from an ethical and AI safety viewpoint. Bommasani et al. Introduced the name foundation models to describe the recent paradigm shift that has taken place. The rationale behind this naming is that terms such as pre-trained model and self-supervised model do describe the technical attributes of these models. However, they do not capture the paradigm shift that is taking place. Language model, on the other hand, is too narrow, since foundation models go far beyond language. Names such as general purpose model and multi-purpose model capture the flexibility but do not capture the unfinished nature and need for adaptation, while task agnostic model captures the manner of training but not the implications for downstream tasks. For these reasons, the term foundation models is chosen to describe the emerging paradigm. The term foundation aims to describe the role that these models play. A foundation model is incomplete by itself, but serves as a common building block for task-specific models constructed through adaptation. The word foundation also implies the significance of architectural stability, safety, and security, since well-constructed foundations are a solid bedrock for future applications, but poorly constructed foundations are a recipe for disaster. At present, we still know little about the nature and quality of the foundation that foundation models are in fact providing us with, so it is too early to say whether the foundation is trustworthy or not. Consequently, the trustworthiness of these models represents a critical problem for a range of stakeholders, notably researchers, foundation model providers, application developers who build on top of foundation models, policymakers, and society at large to address. Next, we turn to social impact and the foundation model ecosystem. One key reason for discussing foundation models, and indeed what makes them scientifically interesting, is their impressive capabilities. However, what makes them critical to study is their integration into real-world products used by people. For example, Google Search uses models like BERT as a signal to improve search rankings. Using this foundation model brought a number of improvements to performance. To take a concrete example for Google Search, if a user entered the query 2019 Brazil traveller to USA need a visa before the update to include BERT, the search engine would not fully understand that the traveller is going from Brazil to the USA, rather than the other way around. And as a result, it would show results for US citizens travelling to Brazil. By contrast, after BERT was added as a signal, the search ranking was significantly improved, and results were shown that focused on individuals travelling to the United States as intended. One thing that makes this change consequential is that Google Search has an almost incomprehensible 4 billion users, so the behavior of the model has major implications. Given such deployments, it is useful to pause and ask, what is the nature of the social impact of foundation models? In particular, how can we responsibly anticipate and tackle the ethical and societal considerations that they raise? The authors observe that it is often easier to reason about specific system deployments to specific users than it is to reason about the social impact of foundation models in general, particularly when these models could be adapted to any number of unforeseen downstream applications. In order to tackle complex questions about the impact of foundation models, it is useful to make a distinction between research on foundation models and the deployment of foundation models. Most of the public knowledge of foundation models comes from the former category of research on foundation models. This typically takes the form of academic papers, demonstrations, and the staggering progress we've seen on competition leaderboards. However, much of the direct social impact of these models is driven by deployment, with models typically trained on private data using proprietary practices. These deployments can arise through new products, an example of which is GitHub Copilot, which is based on the OpenAI Codex model. However, deployments can also arise from upgrades to existing products, such as Google Search. These distinctions are important because research models are typically not extensively tested, and as such, they may have unknown failure modes. For such models, it is often appropriate to provide warning labels to indicate that the model is not suitable for deployment. By contrast, it stands to reason that foundation models that are deployed and affect people's lives should be far more rigorously audited and tested. In order to make progress in understanding the impact of foundation models, both in research and deployment, it is instructive to consider the full ecosystem that these models are part of, since the foundation model itself is only one component of an AI system. Allowing for some simplification, this ecosystem can be thought of as consisting of several stages. The first stage focuses on data creation. Data creation is a heavily human-centric process. The vast majority of data is implicitly about people in some respect. It is often created by people for other people in the form of emails, photos, articles, etc. It can also be measurements of people, such as genomic sequences, and it can be measurements of environments that people live in, such as those obtained through satellite images. It is useful to note that all data has an owner and is created with a purpose, and that this purpose may or may not include training foundation models. The second stage of the ecosystem relates to data curation. Broadly speaking, data is curated into datasets before it is used. There is no single natural distribution of data that can be practically collected. Even the most relaxed curation strategies require some form of selection and filtering. It's worth noting that ensuring data relevance and quality while maintaining legal and ethical compliance is an important but highly challenging task, a fact that is widely appreciated in industry. The third stage of the ecosystem is the training of the foundation model itself. This is the celebrated centerpiece of AI research, but as we can see, it is only one part of a bigger picture. The fourth stage is adaptation, which creates a system to perform some task starting from a foundation layer as base. This can involve combining many modules, such as restrictions on the output space, classifiers, e.g. those that detect toxicity, and combination with other useful signals. It may be, for instance, that a model that generates toxic content is tolerable if appropriate precautions are taken downstream. Finally, the fifth stage is deployment. Direct social impact occurs through deployment to people. As we've seen, the distinction between research and deployment is a key piece of the puzzle. For example, there may be value in permitting harmful models in research in order to advance scientific understanding with appropriate caution. If deployment is to occur, then staged deployments of the system to a gradually increasing fraction of users may help to flag issues early and partially mitigate harms. Although the social impact of foundation models depends on the full ecosystem in which they operate, it is still valuable to be able to reason about the implications of a single model, particularly since many researchers and practitioners' domain of focus is restricted to the model training stage. This is extremely challenging. It is difficult to reason about model training in isolation, in large part because foundation models are unfinished, intermediate objects, and by their nature they can be adapted to downstream tasks, sometimes in unforeseen ways. 2 points, however, can help us here. The first is a set of surrogate metrics for a representative collection of downstream tasks. The second is to systematically document these metrics, for example, via model cards, to ensure that this information is propagated together with the model. Of course, characterizing the full potential downstream social impact of foundation models is challenging. To have any chance of progress requires a deep understanding of both the technological ecosystem of foundation models and of society itself. Next, we turn to norms, incentives, and the role of academia. We'll look now at the future of foundation models, which have already demonstrated significant potential, but are very much in their infancy. Despite real-world deployment, these models are largely research prototypes that are poorly understood in many ways. In fact, it is fairly safe to say that the professional norms, sometimes described as the ethos of science, are not yet fully developed. This statement may seem a little abstract, so to make it more concrete, let's look at the ethos of science in more detail. As noted by Robert K. Merton in his classic 1942 essay, the term science is often used to describe a number of things. It can refer to a set of characteristic methods by which means of knowledge is certified, a stock of accumulated knowledge stemming from the application of these methods, a set of cultural values and mores governing the activities referred to as scientific, or any combination of the above. The ethos of science relates to the third of these points, and represents the values and norms held to be binding on the scientist. 4 institutional imperatives are taken by Merton to comprise the ethos of modern science. The first is universalism. This is the idea that truth claims, whatever their source, are to be subjected to pre-established, impersonal criteria. Critically, the acceptance or rejection of a claim is not to depend on the personal or social attributes of their originator. In effect, race, nationality, religion, gender, class, and other such attributes are irrelevant. However, it is useful to recognize that science exists as part of a larger social structure, which may conflict with universalism. Historically, this has been particularly the case in times of war. Merton cites as an example the 1914 manifesto of 93 scientists at the outbreak of the First World War, and its subsequent responses along patriotic lines from scientists in different European states. However, it is the aspiration of universalism, as captured in the memorable remark of Louis Pasteur, "The scientist has a homeland, science does not," that represents the dominant perspective in science. The second imperative relates to a form of communism in which the findings of science are assigned to the community. The discoverer of an eponymous law is assigned credit for its discovery, but the law is not their exclusive possession. Instead, its use is open to everyone. Boyle's law may be named after Robert Boyle, but it is not just Robert Boyle who gets to use it. It is partly for this reason that the recognition and reputation associated with being the first to publish an idea plays such a central role in the scientific process. It incentivizes open publication of ideas and diffusion of knowledge. The third imperative is that of disinterestedness. Scientists should be objective and impartial. While historically, such characteristics have often been attributed to the personality of scientists, along with other attributes such as altruistic concern and idle curiosity, it may perhaps be better understood through the lens of institutional incentives. Scientists are humans who will, at least to some extent, pursue impartial judgments to the degree that they are incentivized to do so. Many of the mechanisms of modern science, perhaps most notably the intense scrutiny of peer review and the public reproducibility of published results, provide a fairly strong incentive towards impartiality. Finally, Organised skepticism, and in particular the temporary suspension of judgment and detached scrutiny of beliefs, plays a key role in the ethos of science. This can be thought of as both a methodological and institutional mandate, and often brings science into conflict with other institutions, as Galileo discovered at some personal cost. Returning to the kinds of professional norms that may be relevant in the emerging field of foundation models, there is, as of yet, no consensus on topics such as when it is safe to release foundation models, or how the community should respond to methodological misconduct of various kinds. In fact, at this stage, it is still unclear who will determine this consensus. The technology that underpins foundation models is based on many decades of research, spanning fields such as machine learning, natural language processing, optimization, and computer vision. Notable contributions have come from both academic and industrial labs. However, one striking recent trend is that research on building foundation models has taken place almost exclusively in industry. Bommasani et al. Suggests that the high pace of progress, together with the possibility of centralization, raise issues that may benefit from humanists and social scientists, in addition to technologists. Conducting post hoc audits of ethical and social consequences of foundation models after the design and deployment has been completed is not necessarily a recipe for success. Instead, ethical design could be infused into technological development from the start. Here, it's worth noting that academic institutions typically host the widest set of disciplines under one roof. They bring together computer scientists with economists, legal scholars, ethicists, and many others. Consequently, academia may have an important role to play in developing foundation models. This role could include promoting social benefit, mitigating harms, and determining boundaries such as, for example, when particular actions or deployments should be prohibited. It's instructive to consider the fact that the political economy in which foundation models are developed creates an incentive structure for decision-making at every stage. In some cases, market-driven commercial incentives can align well with social benefit. Unfortunately, they can also lead to underinvestment in scenarios where shareholders cannot capture the value produced by innovation. For example, the Gates Foundation states that in previous generations, the market for vaccines worked well for wealthy countries, but not for low-income countries. In addition, commercial incentives can ignore the costs of social externalities, such as the health of the informational ecosystem necessary for a functioning democracy, or the environmental cost of computing resources. Returning to foundation models, there may be little incentive for companies to create an open ecosystem for developing foundation models that encourages broad participation. By contrast, the research mission of universities is the production and dissemination of knowledge and the creation of public goods. As a consequence, academia can help to ensure that the development of foundation models aligns with social benefit that may not be adequately incentivized commercially. It's notable that academia has not been able to participate fully in the development of foundation models. To understand why, some context is useful. The recent resurgence in deep learning has benefited tremendously from increased open science and reproducibility. Public releases of codebases and datasets have become the norm within the community, while open source frameworks such as TensorFlow and PyTorch have made it dramatically simpler to share code. However, it seems possible that foundation models may roll back this trend to some extent. Foundation models may not be released at all, or may be restricted to limited API access. In other cases, trained models may be released, but the actual training of models may be infeasible for AI researchers due to compute costs. It is possible that some small-scale research on foundation models is feasible within regimes dominated by smooth scaling laws. However, some abilities, such as in-context learning, have only been demonstrated at large scale, and thus it requires scale in order to study them. It is certainly possible to focus research efforts on pre-trained models, and this has been quite productive in NLP, with a wide body of work building on top of BERT. However, it's possible that this may be insufficient to address limitations of models that can only be fixed with better design or training procedures. There are several interesting community efforts such as Eleuther AI and the Big Science project led by Hugging Face that aim to train foundation models in the open. Big Science in particular is currently training a 176 billion parameter language model on the French national Jeanzay cluster. However, it seems highly likely that the gap between private and community efforts is likely to grow rather than shrink. For some technologies, of which foundation models may be an example, centralization forces and barriers to entry are potent. If so, eventually even startups may be unable to compete with established multinationals. An example of such a technology is web search, where there is one product that dominates the market in much of the world. It was suggested by Radinsky in 2015 that an important factor in the dominance of Google is that the value of historical search queries is extremely high in providing better search results, and therefore new search engines, even those with good ideas, simply cannot compete without access to historical user data. One way to close this gap in accessibility for training foundation models is through public infrastructure. For this, it is possible to draw inspiration from large-scale, publicly funded science projects like the Hubble Space Telescope, whose cost was estimated at $16 billion in 2021 by NASA, and the Large Hadron Collider, which had a budget of $9 billion as of 2010. Currently, there are efforts such as the US National Research Cloud Initiative underway, and it remains to be seen what can be achieved here. Another possible approach to bridging the resource gap to industrial labs is to use volunteer computing, where computation is donated by many volunteers from small-scale computers across the world. A classic example of this is the Folding at Home project, which conducted large-scale research on protein dynamics using hundreds of thousands of computers. More recently, the Learning at Home project is exploring similar ideas for training foundation models. This is undoubtedly an exciting direction, though it naturally faces significant technical challenges in order to overcome the high latency that exists between internet volunteers and the high bandwidth required for training foundation models with current techniques. Our last section will focus specifically on the Stanford report on foundation models. Given the broad scope of foundation models, it can be challenging to present coherent research on the topic that spans much of this breadth. It's therefore interesting to see how Bommasani et al. Approached the problem. In March 2021, an informal community was constructed at Stanford University comprising students, faculty, and researchers who had an interest in some element of foundation models. This included not just AI researchers, but also experts in healthcare, law, ethics, and economics, etc., who were interested in how to apply foundation models to their domain, as well as in societal concerns. The construction of this community led to the Center for Research on Foundation Models, CRFM, at Stanford, an interdisciplinary initiative that focuses on this theme. It was noted early on that there were gaps in mutual understanding between participants, as well as an incomplete literature on the topic. The goal of the report was therefore to provide a fuller picture of foundation models, to identify opportunities and risks associated with foundation models, and to establish a constructive vision for future responsible development of foundation models. To meet these goals, the report writing was itself an experiment involving over 100 people from different research backgrounds. Much of the report is a survey of existing work that is gathered into a unified theme to highlight interdisciplinary connections. The report focuses on 4 major themes relating to foundation models: capabilities, applications, technology, and society. The authors note a few caveats. First, the field is evolving rapidly, and therefore much of the coverage is inevitably incomplete. A number of applications of foundation models are discussed in detail, but others, such as music, agriculture, finance, and natural science, are omitted, though these may be just as likely to be as affected by foundation models as the applications that are discussed. Other directions, such as the application of foundation models to neuroscience, cognitive science, and psychology, are undoubtedly interesting and form potential areas of future work. It seems plausible that the experimental nature, large scale, and distributed writing of the report across many groups is one reason for the disclaimer that we noted earlier, namely that not all views expressed in the report are held by all authors. We'll next provide an outline for the topics considered as part of the full report, starting with the capabilities of foundation models. The field of natural language processing has led the way for foundation models, and foundation models now dominate NLP benchmarks on almost every task. There is, however, still a notable gap between the current abilities of foundation models and the full, complex system of communication and thought employed by humans. This gap can be studied through the lens of linguistic variation, in particular, the different styles, dialects, and languages used by humans. It's also worth noting that language acquisition in human children is more sample efficient than training foundation models at present. Using additional modalities beyond text and grounding may help to bridge this gap in efficiency. Linguistic variation and sample efficiency offer possible themes for future foundation model research. The field of computer vision was an early leader in pioneering the adoption of deep learning. Perhaps most notably, experiments in computer vision demonstrated the effectiveness of pre-training on large-scale annotated datasets such as ImageNet, and then transferring the learned features to downstream scenarios. More recently, foundation models like CLIP have shown major gains from internet-scale pre-training on hundreds of millions of images paired with alt text to enable zero-shot transfer for many tasks. It thus seems likely that additional training on multimodal and embodied data may enable further progress on challenges such as 3D understanding and common sense reasoning. Some key challenges remain in modelling, particularly in determining how to efficiently work with video data and in accurate evaluation of higher order capabilities. Other topics worthy of discussion include applications such as ambient intelligence for healthcare and society considerations, perhaps best exemplified by the topic of surveillance, which will exert an influence on the impact of foundation models in future. One of the long-standing goals of robotics research has been to build generalist robots that can perform many tasks across physically diverse environments. However, differently from language and vision, which have benefited from an abundance of raw data, robotics is anchored to the physical world. This means that a key challenge for robotics to use foundation models effectively is to acquire sufficient data of the right form that is conducive to learning. If foundation models work well in robotic contexts, they may allow for the easier specification and learning of tasks by robots. This may in turn enable new applications, such as robots for household tasks, which will heighten the importance of robustness and safety. Reasoning and search problems, such as theorem proving and program synthesis, are among the classical, long-standing challenges in the field of AI research. The combinatorial search space associated with such problems means that traditional search-based methods are typically intractable for these tasks. Humans appear to tackle these problems, at least to some extent, by operating intuitively, and works such as AlphaGo have already shown that deep neural networks can be highly effective in guiding the search space. Humans also transfer knowledge across tasks, allowing them to perform adaptation much more efficiently. Foundation models may offer one route to help closing this gap to human ability, thanks to their multi-purpose nature. Foundation models appear to show clear potential to transform the developer and user experience for AI systems by lowering the difficulty threshold for prototyping and building AI applications due to their strong sample efficiency when performing adaptation. At the same time, they raise the ceiling for novel user interaction as a result of their multimodal and generative capabilities. This suggests a form of synergy in which developers can provide applications that better fit the user's needs and values, while also introducing more dynamic interaction and feedback. It's also interesting to ask, what could a foundation model ultimately come to understand about the data it is trained on? For natural language, different positions can be taken. A tentative conclusion given by the authors of this report is that skepticism about the capacity of future foundation models to understand natural language may be premature, especially where models are trained on multimodal data. We next turn to applications of foundation models. While the research of these models is currently focused in computer science disciplines, their applications have the potential to extend beyond this domain. Here we will discuss 3 applications that represent 3 foundational pillars of society. The first is healthcare and biomedicine. Many tasks in this domain require expert knowledge that is both costly and available in limited supply. This includes healthcare tasks such as caring for patients via disease treatment and biomedical research such as discovery of new therapies. It seems likely that foundation models in these domains may be able to learn from data across modalities such as images, text, and molecules, and could yield benefits in cost reduction by virtue of the fact that their high sample efficiency requires few labels for adaptation. It is also possible that foundation models may enable improved interface design, which would allow patients and providers to interact with AI systems. Other directions include the use of the generative abilities of foundation models for open-ended research problems, such as novel drug discovery. However, foundation models also bring risks. They may, for example, exacerbate historical biases in medical datasets and trials. To make good use of foundation models will require tackling socio-technical challenges with regards to data sources and privacy. It will also demand progress in model interpretability and explainability, and the development of effective regulation for the use of these models in healthcare and biomedicine. The second application domain considered is law. For a number of legal applications, attorneys devote considerable effort to producing long and coherent narratives from contexts that shift over time, a task that involves deciphering ambiguous legal standards. It seems likely that foundation models have the potential to provide benefits in this setting, since there are many legal documents that provide data to train on, and the generative abilities of foundation models could map effectively onto generative legal tasks. However, it's worth noting that major progress is needed to enable reliable reasoning over multiple sources of information, and to use this reasoning to generate not just coherent, but truthful long-form documents. The sample efficiency of foundation models may be particularly valuable here due to the very significant costs of legal experts. From an optimistic perspective, this may enable reallocation of legal resources towards problems of justice and government service. As with the healthcare domain, privacy is going to be an absolutely key concern here. However, fundamental advances will be required with respect to the provenance of the behavior of foundation models and guarantees for the factuality of their generation. The third application domain is the complex topic of education. In this setting, effective teaching requires reasoning about student cognition and will, ideally, reflect the learning goals of students. Foundation models may be able to leverage external information across multiple modalities such as textbooks, diagrams, and videos in order to better assist learning, with potential benefits for generative tasks such as generating problems for students, and interactive tasks such as providing feedback to teachers. The notable sample efficiency of foundation models may also be useful here in enabling adaptive and personalized learning for students. It stands to reason that student privacy will then become a key issue, and other factors that are already challenges in bringing technology into the educational sector may become even more critical, such as unequal access to technology in education and technology-aided plagiarism. We will next give a sketch outline of the technology underpinning foundation models. The first relates to modeling, and the 5 key attributes that underlie foundation model architectures. These are expressivity, which describes the ability of the model to capture and assimilate real-world information, and scalability, which here refers to the ability of the model to effectively handle large quantities of high-dimensional data. These attributes can already be seen in existing architectures, such as the transformer. The next generation of foundation models are likely to focus on multimodality, the ability to consume, process, and possibly also produce content spanning multiple modalities, memory capacity, which refers to the ability of a model to effectively store and retrieve knowledge, and compositionality, which denotes the ability to generalize to novel scenarios in which the model encounters combinations of concepts that may have been encountered separately during training, but never in the combination seen during inference. The status quo for training foundation models is to use modality-specific objectives. Classic examples include masked language modeling for training text models like BERT, and image discrimination with heavy data augmentation for SimClear. It seems plausible that future training losses may involve more principled selection of training objectives by drawing on systematic evidence and evaluation suites, as well as greater domain generality to learn in a unified manner across modalities and sources of data. When choosing objectives, there are several key design trade-offs to be considered, such as the choice as to whether to do generative or discriminative training, or how to represent input data. Future training objectives for foundation models may involve more explicit representations of goals themselves. One way to characterize foundation models is as unfinished, intermediary assets that require adaptation for downstream tasks. Various adaptation strategies have been explored, such as fine-tuning, and more recently, prompting language models with text to explain the task to them. However, Bommasani et al. Suggest that it's useful to consider a much more expansive view of adaptation that goes beyond task specification. This includes using adaptation to alleviate deficiencies in foundation models such as applying temporal adaptation techniques that reflect changes over time in the world, as well as imposing constraints on the model, such as enforcing the right to be forgotten under EU GDPR law. More broadly, expansive evaluation protocols are going to be required that evaluate these broader forms of adaptation, while controlling for the kinds of resources they require, such as runtime and memory, in order to be effective. When it comes to evaluating foundation models, we face the challenge that the model itself is typically at least one step removed from the specific task that we wish to perform, and instead provides us with an intermediate building block. Various new paradigms for evaluation of these models may include directly measuring the inherent capabilities of the model, evaluating task-specific adaptation when controlling for resources and access to the model itself, and broader evaluation designs that go beyond accuracy, accounting, for example, for robustness, fairness, efficiency, and environmental impact. The computer systems available for training foundation models represent a bottleneck in scaling up data size and model size, which so far appear to correlate fairly consistently with improved performance. To efficiently train the next generation of foundation models will require co-design of hardware, software, model, and algorithms. And in fact, this kind of co-design is emerging, with examples such as retrieval-based architectures that are more hardware-friendly and scale more readily. The practical deployment of foundation models will require a particular focus on efficient inference to make good use of resources. Training data is absolutely integral to the abilities acquired by foundation models. This idea of the criticality of data has been emphasized in many places, such as in the movement for data-centric AI, which argues for recognizing the importance of carefully managing and documenting training data. Bommasani et al. Note that to date, the modus operandi for foundation models has been to select training data with unclear principles and with limited transparency over the nature of the training data itself. They therefore suggest that one path forwards is a proposal that they refer to as a data hub for foundation models, which highlights the consideration that must be given to the selection, curation, documentation, access, visualization and inspection, quality assessment, and legal regulation in the data management process. From a security perspective, if foundation models continue to become more widespread, they may represent a single point of failure with particularly high leverage, making them potentially attractive attack targets. This is particularly concerning since existing work has already discovered security vulnerabilities in the form of adversarial triggers that can produce undesirable outputs, and privacy risks such as memorization of training data that may include sensitive information about individuals. In addition to this, the very generality of foundation models opens up the risk of function creep, in which they become used for purposes beyond the intended use case of the original creators. One interpretation of foundation models is to view them as similar to operating systems, in the sense that secure foundation models could provide a solid base on which to build reliable applications, but flaws would have far-reaching consequences. From a more positive perspective with respect to privacy, it's possible that the sample-efficient adaptation of foundation models may mean that they can train from large amounts of public data and only require a small amount of sensitive data for effective adaptation in applications where this is appropriate. One long-standing challenge for typical machine learning models is their sensitivity to distribution shift, which occurs whenever the distribution encountered at inference does not match the distribution seen during training. The results to date suggest that foundation models trained on broad data collections may offer greater robustness to a fairly wide range of distribution shifts, which is highly promising. However, foundation models are not a panacea for robustness, with several key challenges yet to be addressed, including the ability to extrapolate across time and a tendency to pick up on spurious correlations derived from the training data. As foundation models see real-world deployment in applications, it becomes increasingly important that the models are reliable, robust, and interpretable. Looking to the future, as models continue to become more powerful, increased care will also need to be given to aligning the models to ensure that they are not deployed with misspecified goals or values. Relatedly, it may be a valuable task to forecast emergent behaviors, such as the ability to deceive or plan strategically, since these may introduce grave dangers when adapting the model to downstream tasks. In principle, learning theory can provide a broad foundation for applied machine learning that provides insights and guarantees to complement empirical findings. So far, the study of foundation models has been almost entirely empirical. In part, this is because classical supervised learning theory is inadequate to address the discrepancy between the training and adaptation phases, which may correspond to different tasks and data distributions. Still, hope remains that any advances in theoretical understanding that can address this discrepancy may yield useful insights for foundation models. Turning next to interpretability, much of the existing repertoire of interpretability methods in machine learning focus on explaining the behavior of task-specific models. However, in addition to their natural opacity stemming from the deep neural networks that underpin them, the fact that foundation models are useful for many tasks and possess emergent behaviors brings additional challenges from an interpretability perspective. Bommasani et al. Propose a lens through which to consider interpretability, which is the one model, many models paradigm. The goal of this paradigm is to determine the extent that one model, i.e. the foundation model, and its many models, i.e. the adapted variants, share decision-making building blocks. Some of the key concepts that merit discussion in the context of interpretability for foundation models are explainability, the validity of post hoc explanations, and the mechanisms that drive model behavior, which may help to clarify whether progress in understanding the foundation model will transfer to progress in understanding their adapted derivatives. Finally, to fully understand the implications of interpretability, it is valuable to consider the societal impact of interpretability and non-interpretability. The fast rollout of foundation models across a range of applications may have a broad range of implications for the health of societies. As we noted earlier, these models are particularly challenging to reason about because, unlike task-specific systems, a foundation model may have many downstream uses. Here we'll mention 6 themes that can shed light on the societal implications of these models. First, a number of studies have demonstrated that machine learning has the potential to contribute to and amplify social inequity. For foundation models, which may continue this trend, it can be useful to separate intrinsic biases, which are biases present in the foundation model itself, and extrinsic harms, which are harms that arise in the context of specific applications. One key technical challenge for foundation models is source tracing, in order to understand the ethical and legal responsibility for the actions of a foundation model. In order to address these challenges, Bommasani et al. Consider proactive interventions, which can include techniques such as counterfactual data augmentation and reactive recourse, which includes mechanisms for feedback propagation of moral and legal responsibility. Next, we turn to misuse, which is defined here as the use of foundation models as technically intended, e.g. to generate language or video, but with the goal of causing societal harm, such as generating disinformation or deepfakes for harassment. It is possible that foundation models may make misuse easier by lowering the barrier to entry to automatically producing high-quality, machine-generated content that can be personalized and adapted for different groups. For example, disinformation actors could target generation of articles across different demographic groups in order to maximize their effectiveness. On the other hand, foundation models may also provide tools to help efficiently detect misuse. Another characteristic of foundation models is that they involve very computationally expensive training runs, which, without careful management, can correspond to significant carbon emissions. One perspective that could be taken here is that such emissions may be reasonable when accounting for the fact that a foundation model is typically trained once and then reused over many applications, amortizing the cost of initial training. Here, Bommasani et al. Suggests that a rigorous analysis of assumptions about how foundation models will be used in practice is beneficial. There are several factors that are useful to consider from an environmental perspective. First, more compute-efficient models, hardware, and energy grids may each contribute to reduced emissions. Second, environmental cost could be included as a factor that informs how foundation models are evaluated to allow comparison with more environmentally friendly baselines. And third, to perform reasonable cost-benefit analyses around environmental impact will require greater documentation and measurement across the machine learning community. Turning next to a legal perspective, it remains unclear how the law bears on both the development and deployment of foundation models. Various forms of legal and regulatory frameworks will be required for foundation models, alongside those for AI more generally, in order to constrain, influence, and benefit practices in development and deployment. In the US setting, Bommasani et al. Highlight the important issues of liability for model protections and protections from model behavior. In both cases, legal standards will need to progress in order to account for the unfinished nature of foundation models compared to existing user-facing, task-specific models. From an economics perspective, it seems likely that foundation models may have a substantial economic impact, thanks to their novel capabilities and potential applications across a wide variety of industries and occupations. As part of this report, the authors conduct initial analyses into the implications of foundation models across both the US and global economy for productivity, wage inequality, and concentration of ownership. Finally, the widespread adoption of foundation models poses ethical, political, and social concerns. In particular, there are ethical issues that are related to the scale of application of foundation models, such as homogenisation and concentration of power. Consequently, it's of interest to consider what the role of norms and release strategies associated with foundation models may be in addressing these issues. It's useful to note that the terminology and interpretation of foundation models that we've discussed here offers one particular framing of recent AI developments, but it is by no means the only perspective. A number of critiques and responses have been offered to the Stanford report. I'll mention just a few of them here to provide extra context. One important caveat: the responses I'm summarising have been assembled by the authors of the report, which represents a kind of filter, and this collection of critiques is by no means exhaustive. The first, by Sue Lynn Blodgett and Michael Medeo, focuses on the risks of foundation models in education, and suggests that the Stanford report, which observes that foundation models may be uniquely well suited for scaling across educational domains and contexts, does not sufficiently consider the risks of harm as a part of their all-encompassing view of foundation models for education. They highlight 4 sets of risks that foundation models pose in an educational setting. The first are risks of educational technologies at scale. While often well-meaning, arguments for deploying large models as being for the student's benefit are often used to motivate surveillance technologies in education. Scaling is also advocated for in order to reduce costs through economics of efficiency, but historically, this has not necessarily benefited all learners. We can look to examples such as educational radio, TV, and computers as technologies that bring second-order effects that must be considered. These can include potentially dehumanizing learning experiences and devaluing the role of teachers, and as such, there has consequently been widespread resistance and opposition from teachers and others against the adoption of such technologies. Second, there are risks of homogenization from foundation models. The use of these models may lead to homogenization of pedagogical practices, ideologies about learning, and educational content, potentially in a way that strongly entrenches the status quo. A key issue here is the role of training data, the vast text corpora that are used to produce these models, which have many issues, and may, for example, reproduce ideologies about what is valuable for students to know. A third set of risks relates to the limited role of educational stakeholders in the development of foundation models, who may have little say in key upstream design decisions. This is quite at odds with frameworks from educational philosophy, in which learners' interests and needs shape teachers' choices about what and how to teach. A fourth risk stems from the expansive and totalizing vision of the role of foundation models put forward in the report. This paradigm requires that teaching and learning is formalized in a way that is legible to foundation models, without considering the possible risks of formalizing teaching and learning in this way. More broadly, Blodgett and Madeo suggest that claims that foundation models have the potential to radically transform teaching and learners in a way that benefits learners should be approached with a critical eye. A second critique from Jitendra Malik begins by noting that, clearly, large language models such as BERT have been very useful, and that the pre-train and fine-tune paradigm has merits, though we should not forget that there are big risks to training these models on uncurated data from the internet. However, Malik takes issue with the idea, evoked, perhaps more strongly than the authors intended, by the report and the name foundation models, which suggests that these models are a template for all of AI research. He subscribes to the embodiment hypothesis of learning, widely held in cognitive science, which is the hypothesis that, among other things, intelligence emerges from the interaction of an agent with its environment, and as a result of sensory-motor activity. Malik does not argue for slavishly following human baby development, but points out that concepts like interaction, grounding, acting in a physical world, etc., are important components of AI. Foundation models developed to date lack any form of sensory-motor grounding, and as such, Malik suggests that they are better thought of as castles in the air. They are useful castles, but they float in air without this grounding. He suggests that a lesson from the history of AI is that we consistently overinvest in the current paradigm and are not sufficiently alert to the emergent new idea in some neglected part of the intellectual landscape. While it makes sense for industry to focus their efforts on these models while they produce good results, academia should pursue a more open-minded strategy. Who knows when and where the next AlexNet moment will occur? A third critique is offered by Gary Marcus and Ernest Davis, who point out that a foundation, in its usual sense, is a bedrock upon which something complex is built. As a classic example, programmers can build on operating systems thanks to the reliability with which it performs operations. A foundation model for AI should provide something similar. It should use information reliably. It should reason reliably. If it interacts with humans, it should be able to interpret human communications, etc. But we are a long way from having achieved this. Foundation models have many issues, and instead provide us with something more akin to stochastic parrots that do a decent job of mimicry, but lack the depth of understanding that general artificial intelligence will require. Marcus and Davis highlight 5 serious concerns that they have about the report. The first is that the renaming of pre-training large language models to foundation models is misleading. It may sound cool, but the name is not justified. Second, much of the Stanford report rests on optimistic thinking rather than scientific argument. For example, in the central problem of relating streams of input from different modalities, the authors acknowledge the difficulty of the problem, but do not offer concrete proposals for how they can be tackled. A third criticism is that the report reflects what Marcus and Davis call a not invented here attitude. There is little discussion of many lines of relevant research in psychology and software engineering, while classic ideas are reinvented, seemingly without awareness. In general, little effort has been made to learn from the past. Additionally, other forms of machine learning are left in the scrap heap, with no mention of how it might be worth considering the past 60 years of studying machine learning to see how insights could be incorporated into foundation models. A fourth criticism is that the report does not acknowledge that the actual impact of foundation models to date has been modest. Many of the conspicuous successes we have seen in AI have been from specialized systems like Watson, while AlphaGo and AlphaZero were built on specialist architectures for searching the game tree of adversarial games. Finally, Marcus and Davis suggest that the report does not just suffer from tunnel vision, it actively promotes it. They agree with the public comment by Emily Bender that overpromises about foundation models suck the oxygen out of the room for all other kinds of research. This can be an unhelpful signal to send to the entire research field. A fourth response from Girish Sastry notes that much of the discussion around release options for foundation models has focused on the distinction between releasing versus not releasing models. However, there may be many other options in the release design space. Different APIs, at the time of writing, already take different approaches. For example, some, such as OpenAI, allow text-in, text-out access, while others, such as Cohere, provide access to text embeddings. Exposing more of the guts of the model may enable more use cases, but also brings risks and requires that the user be trusted, not least to prevent model stealing attacks, which could entirely defeat the purpose of constraining access. In addition to enabling access for functionality while constraining misuse, there are other considerations. In order to have healthy governance, we need ways to be able to audit models, and perhaps even more important, ways to audit the audits. Further research into the release design space could therefore be tremendously valuable. Jacob Steinhardt suggests that there is room for improvement in the discussion of the risks associated with the emergence property of these models by taking the argument further towards its logical conclusions. Steinhardt suggests that the formulation that we have discussed, i.e., that the behavior of the system is implicitly induced rather than explicitly constructed, is actually a better description for self-organizing systems that are designed to produce emergent behavior. A different definition of emergence, that Steinhardt supports, is the idea of qualitative changes that result from varying a quantitative parameter, a concept that was discussed in detail in the classic Anderson 1972 science paper, More is Different. An important concept in this idea of emergence, which applies not only to self-organizing systems, but also physical systems like ice melting, is that of phase changes, in which behavior manifests quickly at some threshold. We should now expect such behaviors to emerge routinely, and for some to emerge quite suddenly. New capabilities such as hacking may emerge, and there may be little time to respond. Beyond misuse, there are also major risks stemming from misaligned objectives, and we may see the emergence of deceptive behaviours. These ideas may seem far-fetched, but they are the logical conclusions of current trends, so we should act to mitigate them early. The homogenization aspect of foundation models not only creates a single point of failure, but also contributes to inertia, which slows down our reaction to new phenomena. Institutions can take years or decades to respond to new technology, making it particularly challenging for them to be effective. By the time some problems become apparent, machine learning may already be deeply woven into societal infrastructure, having been built on years of subtly flawed training data. We won't be able to start over, and the task will be akin to fixing a rocket as it takes off. A better strategy, perhaps, would be to think ahead and to fix the rocket while it's still on the launch pad. Looking at recent crises such as the pandemic and global warming, the pandemic took a year to reach a full policy response, while the global warming response is still struggling after decades of effort. Machine learning progress is too fast for this to be a viable strategy. We need to think ahead, at least a decade, starting now. One thing that can help is to forecast AI progress. The future is uncertain and unknowable, but forecasting can assist planning by building a picture of future systems. Second, we need to work on mitigation strategies for these risks, such as developing techniques for value alignment. Okay, let's wrap things up with a brief summary of what we've discussed. A foundation model has been defined as a model trained at broad scale that can be adapted to a wide range of downstream tasks. These models are associated with two key characteristics: emergence, in which behaviors and functionality is implicitly induced rather than coded into the model explicitly, and homogenization, in which a small number of models become building blocks for a wide range of tasks. Although we are very much in the early days, it seems highly plausible that these models may have significant societal impact. Thanks to their recency, the professional norms around the development and deployment of these models are not yet fully formed. We also discussed how, thanks to the significant computational cost of training these models, development to date of the largest models has been led by industry rather than by academia. There are several further resources I would recommend looking at to dig deeper into the topic, in addition to some of the critiques we have discussed. The first is the full Stanford report itself, of which this video has focused on the introductory section. There is also a workshop on foundation models available on YouTube, with talks and panels discussing subjects spanning the topics of opportunities and responsibilities, technological foundations, industry and applications, and harms and societies. That's it. We have reached the end. Thank you for your attention.